on Thursday a little bit. And just as a quick reintroduction or a quick recap of that, remember that we focused on two different types of loop control structures. We had a for loop, which of course used the keyword for. And all three of the loop elements, the initialization, the continuation condition, and the increment, were all on the same line. So you had something that looked like this. An index variable, which I'm declaring right here, int I, and this is the initialization. We started at, say, 0. Or what we were doing last week is we were starting it at 1 because we wanted to count up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then you have a semicolon. And then this is your continuation condition. While I, the value of I, is less than or equal to 10, continue doing this loop. And another semicolon. So semicolons come after the initialization and the continuation condition. And then we've got the increment here, and this was new syntax for us. I++ simply adds 1 to the variable I. It's syntactic sugar. It's a way to shorten, instead of having to write I is equal to I plus 1, have two operations there, it's a little bit more. You can shorten that up to simply just I++. And we saw several variations on this. I minus minus, of course, would decrement it by 1. You can use a plus, minus, division, and multiplication with other values as well. And we covered all that on Thursday. Then all we ever did in the for loop was we were just printing stuff out for now. Right? I is equal to %d and the line. Let's go ahead and print I. And when we run this, we see that it goes 1 up to 10. Only after it goes up to 11 does it break out of this for loop and you're done. Okay? We had a similar loop control structure called a while loop, right? And here, the three elements were on different lines. And there is a subtle difference that we'll talk about towards the end today of these two loops. But here I'm going to go ahead and create the variable outside before the loop and initialize it before the loop. Then bound to the while condition, keyword here, statement, is the continuation condition. While I is less than or equal to 10, continue. Inside, all we're going to do is the exact same thing, is printing it out. But now if I did this, we observed at the very end, what would happen here? What do you think? Well, if I just ran this code as is. Let's go ahead and try it. 1, 1, 1, 1, 1, 1, 1, y. We initialize I to 1 up here. While I is less than or equal to 10, we print it out. Do we make any progress towards that termination condition? Do we increment I? No. So up here, I'm going to go ahead and stop it. What we need to do is we need to make progress towards our termination condition, which is just the negation of our continuation condition. You either continue or you terminate. You either keep going or you stop, right? So I++. When I do this, now I have the exact same behavior as before. But one of the key differences with a while loop is that I don't have to do it at the end. I could do it at the top. What's this going to print now? Predict. What's the first thing that this loop is going to print? 2. Why 2? 2. 3, 4, 5, 6, 7, all the way up to 11. Why? We increment it first, right? We come into the loop. The value is I. It is less than or equal to 10, but the very first thing we do is we increment it. So now it's not 1, now it's 2. And the first thing that gets printed is 2. Fast forward. It prints 10. The value is 10. We go back up to the top of the loop here. I is less than or equal to 10, because 10 is less than or equal to 10. I++ goes up to 11, and I've run out of fingers. And then we print it out. Right? So with a while loop, you have a little bit more fine-grained control on when your increment happens. It could happen at the start of the loop. It could happen at the end of the loop, of the loop body, that is. It could happen somewhere in between. Right? So that's a review of those two while loops. And as we just saw, there are some common pitfalls. One of the pitfall that we looked at last week was putting the semicolon here. You don't put a semicolon here. And in fact, if you did this, it would look something, hopefully it would complain about it. And in fact, it does. Why is it complaining about it right here? Oops, sorry. There, highlight it there. Why is it complaining about that? While I is strictly less than 10, do what? Do nothing. And I get stuck in an infinite loop again. Doing nothing, though, this time, instead of repeatedly printing out 1, 1, 1, 1, 1. You can see that it's still caught in an infinite loop here because I have a stop button. Stopping it terminates the program. Now remind me, what did we do on the command line to stop a runaway program? To stop a program from the command line, hit or type control, what was it? C, right? So control, hold down the control key and then type C, so control C, okay? So consider the following code. The code that we did before, where you have yet another infinite loop, right? Where I forgot the increment condition. Again, this leads to an infinite loop. So be careful. Right? Again, to kill an infinite loop, either if you're in an IDE, you hit the stop button. If you're at the command line, you go ahead and hit Control C. There's no need to close your terminal or your console or PuTTY or whatever you're using to get back into it. That'll certainly do it, but that'll force you to log in again, right? So don't force yourself to log back in. Just kill the current running process. Okay. So be careful. Here's another here's another pitfall, I should say. Consider the following code. And to do that, for this, I'm just going to go ahead and cut and paste here. All right, there we go. And for this, I'm just going to go ahead and take it over to REPL. And I want to ask you again to predict what's going to happen with this code right here. Right? So you can start it at 0, you can start it at 1, it doesn't really matter. I starts at 0, while I is strictly less than 10, print it out, and increment it. All right, let's go ahead and see what happens. 0, 0, 0, 0, 0, 0, 0, 0, forever. Why? The keen eye will notice what we omitted here. What did we omit? The curly brackets. Usually you have curly brackets here, an opening curly bracket, and then a closing curly bracket down here. Now the program is still running here, by the way. Let me go ahead and kill it. So why did it result in an infinite loop in this case? Well, if you don't have the curly brackets, this is true of both conditionals that we've already covered and loop control structures. If you don't have the curly brackets, the control structure applies only to the next executable line, only the next one single line. So in this case, while I is strictly less than 10, just do this part, print it. Well, what value did it have? Well, it started out at 0, so we print 0, 0, 0, 0, 0. This is the only, this highlighted portion, if I can highlight it correctly, that's the only thing in the loop because I forgot my curly brackets. This is perfectly valid C, but it's a bad habit to get into. Even if you don't need to write your curly brackets, it's a good practice to do so because eventually you'll hit a case like this where you forgot your curly brackets, everything looks indented, so it all looks like it should be part of the same loop, but it's actually not because you didn't write your curly brackets. So let me go ahead and restore those curly brackets. And now, both lines 7 and 8 are part of the while loop. They will both get executed as part of the loop body. And when I do this, what's it going to print? What's the first thing it's going to print? 0. And all the way up to 9 or 10? 9? Good. Right. It doesn't go all the way up to 10. Why? What's the difference between the other loops that we've written so far? Strictly less than 10. So be careful. You could also be off by 1, and that's our next pitfall. Let me go ahead and add some notes here. The above does not have curly brackets. Right? So only the printf statement is, we call this bound to the while loop. Right? It is best practice to always include the curly brackets even if you don't need to. Now, in this particular case, you absolutely need to. Otherwise, you get caught in an infinite loop. But if your loop control structure only had one thing to do, then you still need to do those curly brackets. For example, the for loop that we started out with, for int I equals 1, I is less than or equal to 10, I plus plus. Printf, let me go ahead and just cut and paste this. There we go. Right. Now this does not require curly brackets. If I leave off the curly brackets, it will do exactly as it did before. 1 up to 10, because there's only one line that you need to bind to the for loop here. But it's still terrible practice to do this. Always, always include your curly brackets, even if you don't need to, so that you never get into the habit of not doing it and then screwing it up at some point. Okay? Always have your curly brackets there. Good style. Okay? Consider the following code. Right? This is actual code that was in a product called the Zune. So has anybody ever heard of the Zune before? Right? It was Microsoft's iPod back, this would have been around 2007, 2008, so about 10 years ago or so. And it was much cheaper. That's why it was a better alternative. It had better software, actually, ironically, better than iTunes. And it also had an FM radio. So, and it was $50 cheaper. But on December 31st, 2008, every Zune froze for 24 hours. Why? As you learned last week, 2008 was what kind of a year was 2008? It was a leap year, right? And as you implemented, there was this function called is leap year that if it gave it 2008, it would return true. If you gave it anything else, like 2007, it would return false. If you gave it 2000, then 2000 was a leap year, I believe. I'm not sure, but it would probably return true there. Okay? This was actual code that was in an embedded subsystem in the Zune player. So December 31st, 2008, that was the last day of a leap year. How many days are in a leap year? 366. So let's start walking through this code. Days is 366 because we're on December 31st, 2008. It's the 366th day. It's strictly greater than 365, so we go into this while loop. Right? Now we're inside this while loop. Is it a leap year? Yes. So this if condition is satisfied, and now we're in this section of code. Days is still what value again? 366. So is days strictly greater than 366? No. So this does not get executed. There is no else condition here. So where do we go? All the way back up to the top here. Right? So days is still 366, strictly greater than 365. It's still a leap year. It's still not strictly greater than. Right? So we continue this process in an infinite loop until we hit January 1st, 2009. How many days is it now? 367, right? Because we've gone to the next day. So 367 is strictly greater than 365. It's still a leap year because it's still 2008 according to our counter. Days is now strictly greater than 366. So finally, after 24 hours of sitting and spinning in an infinite loop, this is now true. We subtract 366 days, so now it's day 1, and we add 1 to the year, so now it's 2009. Right? And this is why every Zune froze for exactly 24 hours, and all you had to do was wait for it to come back. Right? But you can imagine, so what was the fix here? What did they mean to do? What should they have done? Well, an else statement or greater than or equal to 366, because that's what it's actually expecting. It was actually still buggy because it was still off. It would have been 0 day on January 1st or something like that, and then maybe there was another system that incremented up to the first day. But this actual code made it into a real system. Now, nobody cares if your Zune player froze for 24 hours, but Microsoft did have to go into panic mode. They did have to address the issue. You can imagine a holiday, pulling in a bunch of engineers to diagnose the problem, then contacting the company responsible for that subsystem, pulling in all their engineers to find this one bug in this one line in this one system. You can think that maybe this is a couple $1 million, right? When it's all said and done, many hundreds of man hours are put into this effort. They still have to push out a patch, and they lose credibility maybe a little bit, not that much. But there's still an actual dollar amount cost in the millions of dollars possibly that you have to attribute to a bug like this. What could have prevented that bug? What did you do on Tuesday with the when you wrote your is leap year? How did you know that it worked? You tested it, right? And you wrote several test cases. What they didn't do here was they didn't test, or, well, gee, maybe we should test for every day in a leap year. Maybe we should automate this test, because you're not going to sit there and type in hundreds or thousands of tests and make sure that it all works. You make automated tests. They're called unit tests. And that's what you started to do on Tuesday last week with your is leap year, right? If you've got a corner case, a situation that is abnormal, like a leap year or a leap year day, you better make sure that that actually works, right? So that not 4 years away from now, suddenly, everything breaks, right? Now, this wasn't that big of a deal because, all right, so people don't get to listen to their music for 24 hours. But there are some very real bugs out there that have cost hundreds of millions of dollars. One of the classic examples would be the Mars rover from 1999, one of the first Mars rovers that never actually worked because instead of landing on the surface of Mars, it just crashed into it at a very high speed. Does anybody know why? What? Kind of. It's just as stupid. Almost. One system was speaking in metric, like it should have been. One system was speaking in imperial, not like it should have been. And when they talked to each other, there was no proper conversion. So instead of going a certain meters per second, it was going a certain feet per second or something, which of course was completely wrong, meaning that it crashed into the surface of Mars before it could even land, costing $125 million. There were several events like this, and they're all attributable to not properly testing, right? So make sure that you are properly none of your stuff is going to cost hundreds of millions of dollars if you screw it up. At most you'll get a call, or your process will be killed by Scott Chafin, our system administrator. But there are bugs that have cost hundreds of millions of dollars. There are bugs that have cost lives. You can imagine that that if you write a subsystem for, I don't know, for diabetics, where you've got insulin, right? And if you're off by one, or if you've got a negative sign in there, and when it shouldn't be, they don't need any insulin right now, when they absolutely need some insulin, you can see the real risk there, all right, of not testing. You can actually cost lives if you have a critical bug like that. Right? So this was a classic off by one error, right? Where you've got a loop and just you're off by the last iteration, or you're off by the termination condition by one. You used a strictly less than sign when you meant to use a less than or equal to sign, right? And there are bugs like that all over the place. Okay, so it's a classic off by one error. We talked about missing brackets. There we go. Unnecessary semicolons. Okay, so good. Other issues. Right? So nested loops. Right? Often you may need to have more than one iteration, or in particular, you may need to have a loop within a loop. Right? And it's perfectly fine to do that, just like if you have an if condition inside of another if condition. Now you might want to refactor your logic there, because if the year is divisible by 4 and it is not divisible by 100, or it's divisible by 400, it's best to put that into one logical statement rather than having a nested if, right? Then you get into indentation hell, right? If you've got 1, 2, 3, 4, 5 indentations and you're making sure that everything's aligned, that's very difficult code to read. So you want to make sure that your code is not deep, right? You want to make sure that your code is as shallow as possible, that you don't have too many nests. And if you have more than 3 nests, if you have 4 nested loops or 4 nested if conditions, really rethink what you're doing and try to rewrite it. But here's an example. Right? So I'll just go out with a classic for loop here. For int I equals 0, I is less than 10, I plus plus. And then within this, instead of just printing out I, let's go ahead and create another loop. For int I equals 0, I is less than 10, I plus plus. Can I do it that way? How many i's are there now? Oh, here, let's print something out. Printf I is equal to %d and the line I. Right. Well, which I are you talking about? Are you talking about the outer for loop or the inner for loop? That's what we call these things. This is the outer for loop. This is the inner for loop. Which I are you talking about? Let's try it out. Probably work. Yeah, it did work, but it worked for the wrong reasons because of scoping. This will work, and it does what I wanted it to do, but there are two i's here. Right? Which I did you mean? Right? There's an I that's scoped to this loop. There's an I that's scoped to this loop. So let's not do that. Let's improve this code. What should I do? I'll use a different variable name here. What would be j, right? Y. Why j? It's the next one, right? Exactly. Right? You'll find that computer scientists are not all that creative people, especially when it comes, well, at least when it comes to naming stuff. For example, we have C. Why is it called C? The C programming language. Yeah, that sounds better than the truth. Because B came first. I think that there was a programming the full name was BCPL or something like that. I forget what it was called, but it was just called B for short. Okay, well, we've got a new programming language. What should we call it? C. Okay. And there is a programming language called D. There is a programming language called R, but not too many in between. But C++. Right? C++ is also a popular programming language. Why did they name it C++? What's next? I++. You just add 1, right? That's why they called it C++, right? So again, there's no, you might think, oh, okay, that's clever. But no, it's just a lack of imagination that most things are named the way they are, right? All right, so I'm going to have I and j here. I is equal to whatever, j is equal to whatever, %d. Oops, there we go. Now, how is this going to operate? First of all, how many things is it going to print in total? This outer for loop is going to run for I being 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This inner for loop is going to run for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But this inner for loop runs for every iteration of the outer for loop here. Right? So let's go ahead and clear this out and see what it prints. Right? So when I is 0, it'll go through the inner for loop. J is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? All the while, I was stuck at 0. It wasn't being incremented because we were doing the entire inner for loop until the end of that for loop. Then the outer for loop, then it increments at the end of this to I++, which of course is then going to be I is equal to 1. And then we go through the process again, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then I is 2. Then I is 3. Each time we're going through this entire inner for loop. So how many things are printed over here without counting them up by looking at them? 100. The inner for loop executes 10 times. The inner for loop executes once 10 times for each iteration of the outer for loop, which executes 10 times. 10 times 10 will be 100 things. Let's verify this by creating a variable here, total. Right? And then each time we'll go ahead and say total plus plus. And printf total is equal to %d and the line total. And let's see if we were right, 100. Okay, we were right. Darn it. I didn't want to do, we'll look at another example here in a second. But where I'm trying to force an error here, a certain kind of error. But we were right, 100. Right? We actually got lucky. Here's a preview of what I'm thinking about. On line 5, what value does total have? Or here, let me go ahead and put a line between them. On line 6, what value does total have? Good, I see a lot of shrugs here, right? That's exactly the answer you should be giving. Nobody knows. It depends on the compiler. It depends on the operating system. It depends on a lot of things. It's not defined because there is no default value. We got lucky here, and the default value 9 times out of 10 is going to be 0. And so 0 plus 1 plus 2 plus 3, that gave us 100 here. Okay? Let me try one more thing. Double x is equal to 1.5. Let's try this. Come on. Nope. Darn it. All right. Oh, well. It can predict. Let's try it a little bit different. I'm trying to force an error here, by the way. So let me go ahead and call it total is equal to total plus I times j. There we go. Let me see if that works. Okay, nope. Darn it. Okay. I still can't force an error here. But here's another review. Total is equal to total plus something else. How could I shorten that up? Plus equals that other thing, so that I don't have to rewrite the variable every single time. And hopefully this will give us the same answer, 2025. Okay? All right, good. So again, let me go ahead and grab this actual code that was working. There we go. And we'll get rid of this here. Okay? All right. So those are nested loops. And of course, you can go with 3 nests if you want, I, J, K. And as I like that it goes I, J, K. What's next? L. Should you ever use L as a variable? Int L is equal to 5. Why is that not a good idea? What does it look like? What can you mix it up with? 1, right? Now, if you've got syntax highlighting, it's pretty easy to see the difference. But that's actually one of the easiest of mistakes to make, L's for I's, right? In fact, people do it all the time with leet speak. They replace the L's with I's to look cool or whatever. But that's also one of the mistakes that a lot of people make when connecting to their Z drive. It's SMB1, not SMBL. And depending on your font that you're using, it can be even more confusing. Right? So I, J, K, never use L because first of all you're going too deep. Now you've got four nested loops instead, and you probably don't want to do that. Right? Okay. Here's another reason that you don't want to do that. Let me just demonstrate something really quick here. We can go 100, 1 million. There we go. So I won't print anything because I don't want it to print a lot of stuff. But I'll just say total plus plus. There we go. So what should we get out of this? The outer for loop goes 1 million times. The inner for loop goes 10 times each. So what value should I get out of this at the end for a total? 10 million? Right. And we do. Right. You can count the number of zeros there. What if I went with 1 million on this one? 1, 2, 3. Right. What, 1 million times 1 million? It's going to be, what do we call them? Thousands, we call them millions. Millions, we call them quadrillions. Right? So it's not going to fit, obviously, but so we're going to get overflow. But let me just go ahead and execute it. All right. So should I sit here and wait? 1 quadrillion operations. Doesn't sound like a lot in the context of computing, but it is a lot. It is going to take probably weeks to do this, to just add 1 to 1. And you can do the back of the envelope calculations by timing the other one, where we just did 10 million. How long did that take? Time for 100 million, how long did that take? And then you can extrapolate how long this would take. It'd probably be weeks here. But that's for later in the semester. That's why you don't want to nest too deeply, because this is going to be an order n squared operation is what we call it. Because you take the number of operations in the outer for loop, the number of operations in the inner for loop, and you multiply them together. Well, if there are n right here and we n right here, then now it's n squared. You do another loop. Now it becomes n cubed. You do another loop. Now it becomes n to the 4th. Right? N to the 4th is not that big as far as mathematics is concerned, but in the real world, it gets big, right? Way too big. Right? For n being 1,000, again, it's going to take weeks to do that. Okay. All right, so that's why you don't want to nest your stuff too much. Another issue is for loops versus while loops. Right? So here's a fact. It's a non-trivial fact if you want to get technical, but fact: any for loop can be rewritten as a while loop, and vice versa. In fact, we also have do-while loops, and some languages have for-each loops. So in some languages, you have for-loop control structures. I'm not going to cover those two because do-while loops are fragile, and the C programming language does not have for-each loops. All right? So why do we have so many loop control structures when you can do one thing one way? All right, let's just go ahead and get rid of for loops. Let's only have while loops, or maybe you're a while loop person. Or maybe you're a for loop person. Let's only have for loops, and let's go ahead and get rid of while loops. Why do we have two different ways of doing something? Why do we have two different ways of adding one? Yeah. Syntactic sugar, exactly. It tastes a lot better if it's more natural, okay? And there are situations where it's more natural to use a for loop, and it's a little bit less natural to use a while loop, and vice versa. Right? In general, you use a for loop when you know how many, even a variable number of iterations you are going to execute. Right? And in general, you use a while loop when you don't know, up front that is, how many iterations you'll execute. Right? So what I mean by that is take a look at what we've been writing up to this point. Take a look at this. Let me go ahead and restore just this regular old for loop here. Right? And we do something in here. Whatever. All right? I know that I'm going to be executing this loop 10 times. So for I running from 0, I is less than 10, I plus plus, do this thing. Right? Because I know that there are going to be 10 iterations. You can make this a little bit more general by creating a variable, setting it equal to 10, and then resetting it if you want to. You can read this in from the user rather than hard-coding it to 10. Right? But it's still the same idea. I know exactly how many iterations I'm going to be executing. I'm going to be executing this n times. N is a variable, but it is a fixed variable as far as this for loop is concerned. Right? So if you know up front that I'm going to be executing this for 5 times, or 10 times, or n times, where n is a variable, then you go ahead and use a for loop. It's more natural. For I running from 0 up to 1, or up to n, do this thing over here. Right? But while loops are for when you don't know up front how many iterations. It depends on the input. This could run for 5 iterations, or it could run for 3 iterations, or it could run for 17 iterations. And while loops are more natural then. Right? And as an example, consider the following. Write a loop to compute how many digits are in a given number. Okay? So let me go ahead and come over here. And let's go ahead and get rid of all of this. And here's my number. Int x is equal to, I could do 1, 2, 3, 4. How many digits are in that? 4. I could say 1, 2, 3, 4, 5, 6, 7. Right? How many digits are in that? 7. Right? If this is truly a variable, and I don't know at compile time how many numbers, how many digits are in there, then I need to write some code to figure that out. Right? And it's more natural, in this case at least, to use a while loop. Now, first of all, what's the real answer here? Best answer. You all just did your assignment 1. So how did we do it in there? Int number of digits. Does that look familiar? Is equal to log base 10 of x, and then we truncated this to take the floor, and then you add 1 to it, right? And printf digits is equal to %d and the line number of digits. There we go. And of course, we need to give this a value 1, 2, 3, 4. Let's go ahead and try that out. And what am I missing up here? Include the math library. There we go. And so this should report 4. Hey, great. What about 5, 6, 7, 8? 8, 9, 10, 11, 12, 13. What's going to happen there? Well, it's already warning you. Spoilers. Well, now it's 10. Were there 10 digits there? No, there were way more than 10 digits. But what happened? There was an implicit conversion from long to int. This is way too big to represent with a regular old integer. 2.147 billion is your maximum. 2.147 billion, million, zeros, hundreds, I guess. There we go. So this should report 10 digits. Excellent. This is the best answer because it's only one line of code and you're done. What if we don't have the math library? I'll initialize this to 0 there. So that was the best answer. How can we figure this out? Well, let me go back to the simple example here, 1, 2, 3, 4, and let's start figuring this out. What if I were to divide by 10 and then rely on integer truncation to get rid of that 0.5? So divide by 10, you get 123.4. Ignore that 0.4. Okay? And how many times have I done this so far? 1. Divide by 10 again, and then use integer truncation to ignore the 0.3. Oops. And keep a counter on your other hand over here. 2. Do that again. 3. Do that again. And now what am I left with? 0. And I've counted up to 4. How many digits did it have? 4. Right. So all you need to do is divide by 10 until you get to 0. Now, if it has 4 digits, this idea of this loop means that you'll execute this 4 times. If it has 5 digits, it'll execute 5 times. Do you know up front, just having x, where x is read in from the user, do you know how many digits are in it? No. That's what you're trying to figure out, right? So let's go ahead and write the code to do this. And I will hard code it to 1,234 so that we can see that we're right. All right, so help me out. What kind of a loop are you going to want here? You don't know how many iterations it's going to go up front. So let's do a while loop. Right? Okay. While what condition? Now, when I demonstrated this, you divide by 10 and ignore the fraction. You divide by 10, ignore the fraction. Divide by 10 until you get to 0. So while x is greater than 0, or not equal to 0 if you really want to. We'll talk about that in a second here. Divide x by 10. X is equal to x, divide by 10. Now, x is an integer, 10 is an integer, so integer truncation takes over. That 0.4 is ignored, that 0.3 is ignored, that 0.2 is ignored, etc. So we're good there. Is there a way to shorten this up, though? X divided by 10, divided by 10, divided by 10. Divided by equals 10. Okay, good. Now this will run, but of course, number of digits is 0. Why? What was the other part of my loop that I was doing on my hand over here? I was keeping a counter of how many times I iterated through this loop. So you don't need another counter, number of digits plus plus. And now when I divide by 10, right, then I add 1 to number of digits. Add 1 to the number of digits, add 1 to the number of digits. And 4 is my answer, just like before. But now I'm not using the math library. I should get, what should I get here? 8. Okay, good. Here, I'll throw it for a loop. Negative, whatever that number is. What should I get here? 8, all right. I get 0, why? It's less than 0 already. So while x is strictly greater than 0, this never executes. And it has the original value of 0 here. So let me go ahead and make it not equal to 0. And in this case, I can take care of positive numbers and negative numbers. I'm just converging onto 0 when I do this. Right? Great. Is there some other test that I should probably run? A corner case. A case that may require special handling or alternative handling. 0. 0 is always the guy that we needed to watch out for. Why? You have to do this in calc and you have to do this in algebra too. What do you never want to divide by? 0, right? Because 0 is an exception to a lot of stuff. Let me try it out. All right, number of digits, 0. Well, okay, is that right? How many digits does it take to write 0? 1. So, would you want to handle that separately? If x is equal to 0, then printf number of digits is 0. Right? You handle that case separately. Else, we'll go into our while loop here and do all this other stuff. Tab over. And there we go. And now we're taking care of this case. Right? 0. Actually, no, sorry, is 1. There we go. Now it's correct. There we go. All right, so that's a prime example of when you would want to use a while loop instead. When you don't know up front how many iterations you're actually going to execute. A while loop, you could do it with a for loop if you really wanted to. You could do it with a do while loop if you really wanted to. But it's way more natural to use a while loop. While this condition is not satisfied, or while this condition is satisfied, continue doing what you're doing. Right? While it's not 0, continue dividing by 10 until you get to 0. Okay? Some other issues would be that a for loops iteration is always at the done at the end of the loop iteration, and you cannot scope, that is declare, an index variable in a limit that is limited to a while loop. Right? And what I mean by that is a for loops iteration is always done at the end. If I had a for loop here, like our traditional for loop what we had before, for int I equals 0, I is less than 10, I plus plus, that I plus plus is always done at the end of the loop. Okay? If I have a printf statement here, I is equal to %d and the line I, right, then this will always execute after that print statement, at the end of the loop right here. Right? Now, you do have some control over this. I hesitate to show you because you shouldn't get in the habit of this unless you're really comfortable with it. You can leave that blank. Right? In fact, all three of these things you can leave blank. You could have a loop that looked like this. Right? What's going to happen here? Yeah, let me go ahead and int I is equal to 42, right? Because I still need the I. So what's going to happen? An infinite loop, 42, 42, 42, 42. Why? There's no initialization condition, but that's okay because I is 42. There's no continuation condition. While nothing, continue. That's why you're getting an infinite loop here. Let me go ahead and back this up. So you can leave this blank, and then now what would happen if I actually executed this, though? 0, 0, 0, 0, 0, 0, 0, 0, 0, forever. Why? Because the update is not happening. You can go ahead and manually do the update inside the loop. Right? I plus plus at the end. This will lead to the exact same behavior as before, 0 up to 9. Or you can change it to the beginning. What will it print now? 1 up to 10 instead. Right? So you do have some control, but it's kind of the usual way that you do this is with an I plus plus up at the top. Right? So you can get the same behavior of a while loop, but you can't, if you do have a non-blank iteration statement here, it always happens at the end of the loop. Likewise, my second point was that you cannot scope a variable to a while loop. What I mean by that is when I create this variable I here, I does not exist at this point. I does not exist. It is out of scope. Right? If I tried to print it, there would be definitely a compiler error here. Let me go ahead and just cut and paste this. There we go. And it's complaining. Why? I does not exist. Okay? So let's try to do the same thing for the while loop and limit the scope of the index variable to the loop itself. Int I is equal to 0. Well, int I is less than or equal to 0. There's something it doesn't even make sense because you only have the continuation condition here. Int I is less than or equal to 0, you can't do something like this, right? You can't declare a variable in here because it's expecting a Boolean expression, right? So this is not possible. So in general, you can, if it's more natural to use a for loop, go ahead and use a for loop. If it's more natural to use a while loop, go ahead and use a while loop. When do you know the difference? It's all intuitive as once you get into the habits. Okay. All right. Good. Let's see. So with the rest of our time here, a half hour or so, I've got plenty of exercises that we can do. And then we'll continue with these exercises on Thursday. So does anybody do martial? I don't do martial arts. So, but does anybody do martial arts? Does anybody know what the kata is? All right, the kata is, I'll just go appeal to a pop culture movie. What did Miyagi-san do to Daniel in Karate Kid? Right? What did he have him do to practice? Wax on, wax off. Why? This is a kata, right? Getting into a move or a routine that then muscle memory means that you can do it right away. That it becomes second nature to you. These movements, then you commit them to your muscle memory. This is coding kata. That anytime you want to get practice in new programming language, take out some common things that you do in other programming languages and just do them all. For example, these are just exercises that get you into the habit of writing these things once you do it over and over and over again. Print a list of even integers from 0 up to n, 1 to a line. Print the same list but delimited by commas. Print a list of integers divisible by 3 between 10 and 100. Print the total as well. Print all positive powers of 2, 1 up to 2 to the 30th. Print all even integers 2 through 200 on 10 different lines. Okay? So let me go ahead and I'll go back and forth here. Let's go ahead and do this first one. Print a list of integers. I can't write it like that, but I'll print a list of integers, even integers, 0 up to n, but 1 to a line. So I'm going to have to create a variable here. I'll just set it equal to 10 for now. Help me out. What is more natural here, a for loop or a while loop? Do I know up front how many iterations I'm going to go up to? Well, it's variable, right? So a 0, 2, 4, 6, 8, and up to and including n. Right? So 10, right? So do you know how many iterations that was? I mean, it's kind of fixed, right? So for loop or while loop? Yeah.
So if we end up using a different loop than what your method you're supplying us, would we be turned off for anything?
Not as long as you're as long as it works and as long as you're consistent about it, I suppose. But you'll get into the habit of, a for loop, why'd you do that? Or you'll even look back, say 3 weeks later, why did I do a for loop? Because you got in the habit of recognizing when one is more natural over the other. Right? All right, so I'm going to go with a for loop here. Why? Well, because it's pretty straightforward. You're going to go from 0, 2, 4, 6, 8, all the way up to n. Right? Meaning that you know up front that you're going to do roughly n divided by 2 iterations on this. So I'll start I where? Where should I start I? Where do I start? Even integers? Is 0 even or odd? It's even, so should I start at 0? Yeah. Right. I is less than n. Okay. I plus plus. Now printf, I'll go ahead and try it like this. I is equal to %d, or just %d, and the line, I. What's this going to print as it is right now? So we start at 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. Why? Well, n was 10 here. Well, 9 is strictly less than 10, so it executes. When it goes up to 10, though, then it breaks out of the for loop because 10 is not strictly less than 10. Okay? That's not what we want. We only want even ones. So what could I do? Here's my first idea. If I mod 2 is equal to something, then I'll print it out. equal to what? If you divide by 2, you're going to get a remainder of either 0 or 1. Which one indicates that it's even? 0. So if you divide by 2 and there's no remainder, that means it's even. Okay. 0 up to 8. We're still not quite there. Okay. So what do I need to do? I'm off by 1. I'm like that Zune guy that programmed that terrible loop. I'm off by 1. I'm off by the 1 on the tail end of this. I need to go up to and include 10. So what should I do? Less than or equal to. And when I do that, I get what I want. 0, 2, 4, 6, 7, 8, 10, right? Let's just test this to make sure. Well, what if it goes up to 20? I should get 0, 2, 4, 6, all the way up to 20. That works. What if it goes up to 21? Or let's go lower, 11. Should I print 11? Nope. And it doesn't. Right? Okay. So is this the best way to do this? Think about what it's doing. 0, oh yeah, that's even, print it. 1, no, that's not even, don't print it. Don't do anything. 2, that's even, print it. 3, that's not even, don't print it. I'm doing a lot of nothing, right? Maybe there's a better way of doing that. Maybe there's a better way of doing nothing. Right? Skip the doing nothing. Right? Instead of checking to see that it's 2 so that you can print it out, how could I modify my actual loop control structure here to only go 2, 4, or 0, 2, 4, 6, 8? Instead of going up by 1, what could I go up by? By 2's. I is equal to I plus 2. That'll work. And now I'm not doing that nothing. Is there a shorter way of doing this? Plus equals. And I think that that's the best solution right there. Right? Although be consistent with your white space. Okay? And let's make sure that it still works on all of our stuff. This is called ad hoc testing, where you're just putting in numbers to make sure it works. That's not the best kind of testing, because if I go and make a change, like I've made 3 or 4 changes already, then I have to go through all that testing again. Whereas if I had written a test suite like you did in lab on Tuesday last week, then all you have to do is hit a button and it reruns all your tests. Did you break anything? Right? No, I didn't break anything, so great. That's an improvement. Right? Okay. That's the first one. The same list, but delimited by commas. All right. Copypasta. Not a good idea in general. But instead of n-line characters, I'll go ahead and put in a comma space. So that when it prints out, I'll rerun it again here. It prints out 0, 2, dot, bop, bop, bop. Except for, that's kind of annoying. All right. I don't want that last comma there. That's not even an Oxford comma, right? That is a needless comma at the end. So help me out. How can I fix that issue? Let me go ahead and put this down to 10 so it's not printing so much. How could I take care of that last comma and not print it? I could put an if statement here, right? If I is less than n, then go ahead and print it with a comma until you get to that last one. I'm already not liking this because lots of typing. Printf, percent d, no comma. We'll go ahead and end the line, though. Else like this. That'll probably work. And you see that it did go to the next line here. Right? That's a whole lot of code, repeated code. I don't like that. Is there a better solution? What if I handled the last iteration separately? Right? Now, this is not correct because now I do have to put I outside the loop here. I'll start it at 0, but it's the same as here. Right? All right, let's see if this works. And you can see, let me run it again. Right? So, I want to end the line instead. There we go. So 0, 2, 4, 6, 8, 10, 12, and then ends line. Well, I fixed my formatting issue, but then fixing one issue, now another issue has popped up. Is it going up to n anymore? No. We broke out of this loop. Right? When it hit 12, well, 12 was no longer less than or equal to 10, so it has a value of 12 over here. How can I take care of this now? Don't go all the way out of the last iteration. Go one less. Right? And now it'll work. I was off by 1 again. Right? And I just need to take care of that last iteration separately. A lot of problems have a solution where every 99% of it, every iteration is the same except for that last iteration, or maybe except for that first iteration. In which case, go ahead and handle that separately outside the loop before you begin. Or at the bottom, go ahead and handle that separately after the loop. Right? Now, does it work? Ooh. Again, we need to go through all of our tests again. Does this work? Nope. Yeah. I could, but then I wouldn't. Then I wouldn't have the last value I wanted here. You could do something like this, I suppose, where you don't have I here and you just ended up printing n, right? But that's not going to be correct because now it's 11, and that's not what I want. I could add another if statement, but keep it simple, right? Okay. Nope. Let me go ahead and restore it to what it was before. I want to skip that last iteration only if only if it needs skipping. So you can manipulate the variables as well if you want to. Like -1. Don't go all the way. Now it's going to be 10, right? This will. Sorry. No. In this case, let's run it. This is still wrong. Right? Still goes up to 12. If you're going by 2s and you want to make sure that you skip the last iteration, what should I subtract off instead? 2. And now it should work for 11. It should still work for 10, hopefully. Yay. It should still work for 21, or 21. Goes all the way up to 20. And it's only line breaking here because I don't have too much room here. Not enough real estate. 20, I should get the same answer. Nice. Okay. So remember that you can always manipulate the variables. You can always manipulate whether or not you take care of the first iteration separately, the last iteration separately. Okay? All right. Print a list of integers divisible by 3 between 10 and 100, and a total as well. Right? There we go. So print a list of integers divisible by 3. So I will go with 4, another for loop, right? Because I know that I'm going to be going from 10 up to 100 or something like that. Int I is equal to, where should I start out now? Is 10 divisible by 3? No, why should I start at 10 then if you're not going to print it? Is 11 divisible by 3? Nope. Is 12 divisible by 3? Yeah, that's where I should start. I is less than or equal to, what's the last one that I'm going to print that's divisible by 3? 99. Right? I plus plus, go up by 1s. If 3, what's the next one that's divisible by 3? Or sorry, 12, what's the next one that's divisible by 3? 15, 18, right, 21. I'm going up by 3, 3, 3, 3 each time. So I is equal to I plus 3, or shorthand, plus equals 3. Oops. Printf %d, comma. There we go. And I won't worry about formatting here because you know how to handle that. All right, and it prints 12, 15, 18, ... all the way up to 99. But we also want to print out a total as well. Right? So int total. Right? Total is equal to total plus I. Right? Is there a shorter way of writing that one? Total plus equals I. And we'll print it out. Printf total is equal to %d and the line. Total. Right? Now take out your calculators, and what is the sum of all all 12, 15, 18, ... I don't know. Let's find out. Total is 1665. Well, you could do a lot of manual, pen and paper stuff, where you could pull out your calculator, type a lot of stuff. Otherwise, another excellent tool is Wolfram Alpha. Right? Sum these numbers. Really has to think about that. Okay. That's a number. Nope. Sum of, come on, you're smarter than that. There you go. What's the answer? 1665. You just have to help it out a little bit because it's not that smart. Right? It's smart enough to figure out if you speak its language or speak as close of it to English as possible, right? Again, what's the best programming language? Why do we start with C in this course? Why didn't we start with Java or Python? Python's pretty popular. Or why didn't we start with R? Lots of data and statistics people love R right now. Why didn't we start with C#? Everybody loves building Microsoft apps. Why didn't we start with Objective-C or Swift? Everybody likes building iOS apps, right? Does it matter? Among all those programming languages, which one's the best? Exactly, none of them. They all suck, right? What's the best programming language? English, plain old natural language, right? Every iteration of a language, going from binary up to assembly, up to higher level programming languages, is nothing more than an attempt to try to get programming closer and closer to natural language. We can't even get computers to understand natural language, much less be able to program in it yet. So that's still a pipe dream. But something like this is pretty close, right? Some of these numbers, a bunch of common delimited values, right? Okay. And I'm pretty sure that we got 1665, right? 1665, excellent. All right. Another one. Print all positive powers of 2, 1, 2, 4, 8, up to 2 to the 30th. So again, if I'm naive about it, I could do a for loop for int I equals 2. I is less than or equal to 2 to the 30th, which is going to be, tell me what it is, Wolfram Alpha, 2 to the 30th. It's going to be that number right there. Cut, paste, I plus plus, and if is power of 2, then print %d and the line I. Now, obviously, this is not. This is the ideal programming language, right? This is natural language, but it's not going to let me do something like this, right? And also, would you want to do something like this? You want to do 1 billion operations just to print out about 30 numbers? No, that's insane. So let's rethink this. I, and I. Right? Well, what is power of 2? 2 to the 0 is going to be 1. Right? 2 to the 1 is going to be 2. 2 to the second is going to be 4. 8, 16, 32. Right? All I'm doing is iterating by 1 on the exponent. 2 to the I. Right? So let me go ahead and start I at 0 up to 30, I plus plus. Now I'm only doing 31 iterations. And I'll go ahead and compute the ith power, right? Compute 2 to the I. Oops. Well, I can't do that 2 to the I. I can't do that. I don't have the caret in C. I do have the caret, but it means a bitwise exclusive OR operation. It doesn't mean power. What do I have that gives me a power? A what? Pow, right? X is equal to pow. And do I still have the math library? Yes, I do. Good. Pow of 2 to the I. And printf, x is equal to %d and the line, x. All right. So did it work? 1, 2, 4, 8, 16, 32, ... all the way up to, and there's the number that we copied from Wolfram Alpha. I'm convinced that it works. Let's clean it up a little bit and make it even better. Before I do that, though, can I go one more? Let's find out. Negative. What happened there? It went 1 too big. All right? Remember, the maximum value that we can represent is 2.147 billion. That's 2 to the 31st minus 1. That minus 1 kills us because if we go to 2 to the 31st, like I wanted to do up here, that's 1 more than we can do. And if it's 1 more than we can do, we've got overflow, and it comes back around to the negative values. So we can't do that. Remember, overflow. Let's clean this up a bit. I don't have access to the math library anymore. How can I compute 2 to the I? Well, what were you doing this entire time? You started x at 1, then you doubled it, now it's 2. You doubled it again, now it's 4. Doubled again, 8. Right? What if I just did that manually, multiplied by 2 each time? Let me go ahead and create x over here. I'll start it at 1. I'll print out x. And then I will double x. Right? Or I don't want to say double because double has a different meaning here. Multiply x by 2. Right? X is equal to x times 2. Okay? And I get the same exact result without relying on an external library, doing some numerical interpolation algorithm that we're going to do on Thursday. Right? Okay. That looks good. Further improvements. Times equals, shortens it up. That's nice. Further unimprovements. What if I wanted to multiply by 2 first? What is this going to print out? So I comes in here. X is 1, right? Times 2. So the first thing that it prints is going to be 2. What's the last thing that it prints? That weird-looking number there, negative. Why? Because we're off by 1. Now, we're not just off by 1 on the end or the beginning, but we're off by 1 on an entire shift. We need to shift everything down to what it was before by changing the order of operations within the loop. And when I do this, I get what I was looking for. Okay? So the key thing to take away from this is you can have a loop control structure that depends on I, going from 1, 2, 3, 4, 5, 6, or whatever. You're not bound by just that number. You've got the ability to create another variable, right? And use that a counter variable. In this case, an exponent variable where you're just doubling it each time. You can have as many variables as you need. So you're not just limited to the I variable that is part of the loop control structure here. Okay. Last one would be, here we go, prints all even integers. Oops. Print all even integers 2 through 200 on 10 different lines. So 10 numbers per line. Okay. All right. Help me out on this one. 2 to the 200, so that's pretty straightforward. I will start at 2, while I is less than or equal to 200. And what was the trick that I used before? Just go up by 2's. Right? Okay. Printf, %d, comma, I. Right? That'll work, except for they're all on one big, giant, really long line. And you can't see that because, of course, I don't have enough real estate here, so it's not gonna. It's putting it all in one line, but then breaking it up so you can see it all. Okay. How can I get 10 to a line? So what I want is 2, 4, 6, 8, 10, 12, 14, 42. Well, no, it's off now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then I want to go to the next line instead of printing a comma. So what kind of a, yeah, go ahead. I can put in a condition, right? If I mod 10 right, is equal to 0, there's no remainder, that it's divisible by 10. So 10, 20, 30, 40, except a lot of those things I'm not going to print, or maybe I am. Then I will go ahead and printf an endline character. Right? I'll put that at the end, of course. Oops. So print the number. Then if you are at the point that you should go to the next line, then go to the next line. All right, kind of got there. Right? 10, 20, 30, 40, 50. But was that 10 to a line? That was only 5 to a line. Right idea, just off by 1 or off by something. What should I do instead? Mod 20, right? If it doesn't work, just try number after number until it does work, right? No, don't do that. right? Think it out. Think it out on a piece of paper. Work it out on a piece of paper if you need to. We call that whiteboarding, right? And this is why we allow and encourage collaboration in this course, because you need two people to whiteboard. One person, goes up to the whiteboard, starts writing out ideas. The other person's sitting there, and they see, no, that's a misconception. They've reached a consensus that, this was our misunderstanding, right? You whiteboard it together. You write it down, not on a piece of paper, because a piece of paper is one person kind of thing. You whiteboard it or blackboard it, right? Okay. All right, so did that work? Yes. One thing that we might do is, I don't like those commas at the end, maybe we need to add another check there to see if we're going to print an inline character instead of a comma, but I'll leave that as an exercise for you. Right? Any questions? Because when we come back next time, we'll write a few more programs here. We're going to write, including the classic FizzBuzz program. Now, this was in one of your required readings a couple weeks ago. It was a lamentation from a bunch of industry people 10 years ago that all of these applicants that they would get for their developer jobs or software engineering jobs, and every single one of them failed to, once they were hired, they passed the interview or whatever, every single one of them actually failed to perform. And it's because they were all lying about their own abilities for some reason. Somehow they got through the cracks. And so what they did is they started to have very simple filters, basically. And FizzBuzz is one of these filters. Here's the problem. Print out numbers 1 to 100. Print out the integers 1 to 100. Except for if it's divisible by 2, or 3. If it's divisible by 3, print out the word fizz instead. If it's divisible by 5, print out the word buzz. If it's divisible by 3 and by 5, then print out FizzBuzz. Otherwise, if it's not divisible by any one of those three numbers, then print out the actual number. And at least according to the industry folks, this was able to filter out, they're probably hyperbole, but it was able to filter out like 90% of all applicants. 90% of all applicants couldn't, in the language that they claimed that they knew, couldn't actually program that program. And so this is something I always cover in the 4th week because I want you to pass your interviews. And I want to demonstrate that this very simple program is something that you should be able to do after the 4th week of a CS1 course, not as an interview after 4 years of education. All right, next time.